In this example, we're told a chemical company sells 6 molar sodium hydroxide. A chemist determines the concentration of sodium hydroxide concentrations below, and we're asked to comment on the accuracy and the precision. So before I get into how to do the math here, I do want to spend a few seconds to talk about what the difference between accuracy and precision is. And one way to do that is to think about a bullseye. So accurate values are values that are close to the center of the bullseye. So if you're throwing darts and you hit exactly in the middle, you're throwing accurately. Precise values are values that are close to each other. Accurate values can also be precise. So if these values are all close to each other and close to the bullseye, they're both accurate and precise. But precision, it can happen without accuracy, such in this example here. These values, or these throws, if you will, of darts, are not very close to the bullseye, but they are close to each other. In scientific methodologies, precise values cannot be accurate if there's some type of systematic error. So if you're consistently off, but it is consistent, there may be some type of systematic error or something you're not considering, which would move your values over to the bullseye. Or in some cases, the bullseye may need to move over here, but that's a whole different thing. At the end of the day, the thing to remember is accurate means very close to what it's supposed to be, and precise means very close to each other. And also values can be both accurate and precise. Now to speak about this mathematically. Mathematically, it's a little bit different. Mathematically, for the measure of precision, we use RSD, which is called relative standard deviation, and that's in parts per thousand. And for a measure of accuracy, we use percent error or percent difference sometimes as well, but they're basically the same thing. So we use this, and this has units of, whoops, not 5, of percent. So this is a measure of precision, and this is a measure of accuracy. So we have these two measures. However, in order to calculate these things, there are a couple of other things we need to calculate first. So we have these 5 samples, and we have the molarity of each of the samples. So the first thing we need to calculate the RSD and the percent error is the average, which will have the same unit as the concentrations themselves. In Excel, probably the easiest way to do this is to first hit the equal sign, then type in the word average, then open a parentheses, and simply highlight the data you want to take the average of and press the enter key. So now we get the average of this data. Excel, just like calculators, will not necessarily give us the correct number of significant figures. So here is the average of this data. And just so it's a little bit easier to see, I'm going to put it in the middle of the screen here. So I just typed in average and then hit enter. The next thing we're going to need to calculate is the standard deviation. And that is also going to have units of molarity. In Excel, to calculate the standard deviation, you type in the equal sign, and then the function is stdev, open parentheses, and select the data you wish to calculate the standard deviation of. Again, you are not trying to correct the significant figures necessarily right now, and Excel does give you way too many. Now the relative standard deviation makes the standard deviation relative to the average. The smaller the deviation between the values, the more precise that they are. However, what this does is it relates it to the average. So if you have very large things and very small things, you can compare their relative standard deviations much better than you can compare their actual magnitude of their standard deviations. So for the relative standard deviation, what you want to do is type in the equal sign, and it is equal to the standard deviation divided by the average times 1,000. And the reason 1,000 is it's in parts per thousand. And here you'll see that our relative standard deviation is 10 point something. Typically, you round this to the nearest whole number, and you can do that by clicking this. If you wanted to actually round it to the nearest whole number, you can get more or less digits by clicking on that. So to the nearest whole number here, our relative standard deviation is 10, which is a measure of precision. Next, I want to calculate the percent error. The percent error needs a standard, and in this case, we know the actual concentration that this is supposed to be. So in order to calculate the percent error, we want to take the absolute value of the difference between the known value and the average value. So to take absolute value in Excel, you hit equals and then ABS, open parentheses, 6 or 6.00 minus the average. Once you have that, you want to take the difference between them and divide by the known value, which in this case is 6.00. And because it's a percentage, you do want to multiply by 100. When you do that, you find that the percent error is, is 0.1%. So to show you the formula again, I accidentally hit the wrong button, but here you have the formula again, and this tells you the percent error here. So the precision here is measured as 10 parts in 1,000. This is about 1%. That's not bad. That means the data is all within 1% of each other within reason, and that is fairly precise data. The accuracy, it means it's a 0.1% error. This is very accurate because it's close to the expected value. So now we've mathematically shown what we probably intuitively knew already, because all of these numbers are relatively close to 6, that they're all relatively close to each other, so they're fairly precise, and that they're all relatively close to 6, so they're relatively accurate. So these are measures of accuracy and precision.